This is Viridi. Viridi is an automated environmental monitoring system.
Viridi was developed with the intention of making an environmental monitoring system that is affordable, accessible, accurate, effective, and educational. But why is this important, Stanley?
Thank you, Stanley. Viridi is important because people often feel a sense of disconnection from climate change due to the global scale at which we often hear about it. This global framing leads to unawareness of local environmental conditions, making it harder for individuals to recognize and express concern about the environmental issues that could be affecting their communities. As a result, there's a lack of individual and collective connection and motivation to address these local issues. Environmental monitors can effectively solve this problem. However, they're typically designed for professional use, can be difficult to use, and are prohibitively expensive. An affordable and accessible solution gives everyone the ability to explore and think about environmental data.
But Stanley, how can we implement this?
I'm glad you asked, Stanley. Using a Wi-Fi enabled microcontroller, we can collect data from various environmental sensors. This data can then be sent to a cloud storage platform and accessed from a mobile application. Viridi uses a Firebeetle ESP32 as its microcontroller, an M5 Stack ENV4 unit for temperature and humidity sensing, a PMS 5003 for particulate matter sensing, and a DFR SEN 0321 unit for ozone sensing. The data collected from these sensors is sent to a ThingSpeak server and can be viewed in a connected Android mobile app made using React Native. This allows you to view current and past environmental data from your phone at any time. Now, Stanley, would you mind showing the people at home how to turn the system on and connect it to Wi-Fi? Of course, Stanley. You start by taking the USB cable and connecting it to a power source of your choice. You'll see a blue LED light come on. This indicates the system is starting. Once this light turns off, then you know it's time to connect the system via WPS. You then hold the WPS button on your router until you see the green Wi-Fi signal show up, or some other indication if you're using a different router. The LED on your device should then be blue. This tells us that the system is online and logging data. Now we're going to take a look at the code that's running on the ESP32 and how it all works. The ESP32 code is divided into two main parts, the setup and the loop. This is the setup code. Here we define all the things we want the ESP32 to do each time it starts up. Before it, you also saw all the variable declarations and library imports. These are essentially just things we want to use or access more than once in the code. In the setup, we disable the Bluetooth connectivity of the ESP32 and also lower the CPU speed. This is to save power, and we won't need these features as we aren't performing complex calculations or using Bluetooth connectivity. Next, we have a 10-second delay. This is to make sure when uploading the code to a new ESP32 or testing, we can plug it into the sensors without issue. Then we begin two serial channels. These are text log outputs, one for particulate matter readings, as the sensor uses this serial channel to communicate, and one for debugging. Finally, the setup triggers WPS connection, and once connected, checks all sensors to make sure they are connected and online. The loop code is this section here, and is relatively straightforward. We wake up the sensors and wait 2 minutes for them to warm up, read each sensor, sleep the sensors, send the data to the server via an HTTP request, and then wait 58 minutes. The 58-minute delay, combined with the 2-minute wake-up time, gives us readings roughly every hour. There is, however, a 30-second delay before sending data, so the actual time between readings ends up being 60.5 minutes. If you want to see the full code for yourself, it's all available at the GitHub link on screen now. Now, we're going to take a look at an early data output of the system, so you know what to expect if debugging. When the system is connected to a computer with a data-capable USB cable, by opening the Arduino serial monitor, you can see formatted data outputs from the sensors each time the system takes a reading. Now, Stanley is going to take us through the data storage system used in this project. Now let's explore the ThingSpeak dashboard. This is where the data for our sensor setup is being sent to be stored. There are line graphs for each channel, each of which is tracking a metric, as well as a bar graph for the system's uptime. A green section means the system was online for that hour. You can see here the most recent data point from when we turned the system on. And as you can see from these points, the system logs data every 60.5 minutes.
But Stanley, where does all this data go next? You told us it would be easy to view and explore environmental data in a connected mobile application.
You're right, Stanley, and this is where Viridi's linked mobile application comes in.
The application can be started with Expo Go, as Stanley is showing us here, by simply scanning a QR code, or by using an APK build of the application. This is the main environment screen. You can refresh the data, but as you can see, it hasn't yet been an hour since our initial reading from turning the system on. The colours of each metric are representative of where the metrics lie on their respective scales, and each metric has an informational modal showing more information about it. Each modal contains a summary of the metric and a link to further reading. The temperature modal also shows you the difference in temperature between current levels and the monthly average from 2014. The air quality modal gives you a breakdown of the air quality for each measured pollutant and tells you the different categories and colours of air quality. The humidity modal tells you what the current humidity level is and possible health effects this may cause. The second screen of the application is the data screen. Users can select a metric and period and are presented with two visualizations as well as a statistical summary. The line graph gives a detailed look at the variation over time for each metric, with highlighted points that correspond to the scale. The summary at the bottom tells the user the highest, lowest, and mean values for the selected period, and the bar graph shows averages of an appropriate time for the period selected. For example, hourly averages when the period selected is the past 8 hours.
Thank you, Stanley. As you can see here, all of the visualizations for different metrics and different timeframes correctly retrieve and display data. And as you will see shortly, tapping on a bar shows the current value of the bar in an alert. Now we go over to Stanley, who will tell us about the housing concept for this system.
The 3D model you are seeing here was designed using FreeCAD. It consists of a removable door panel with indents for a flush fit with the main body and uses standard size screw holes, a back mount designed to fit a standard bivy pole as a suitable outdoor mounting solution to keep the housing off the ground to prevent interference from solar radiation. The main shell and door have double louvered slats to protect the sensors inside from the elements, and the inside is divided with an interior shelf into a weatherproof area for the battery and microcontroller to sit, and a mesh-bottomed compartment for the sensors to allow adequate airflow. The dimensions of the model are 200mm wide by 240mm deep and 180mm high. This size was chosen as it comfortably fits the sensor setup and allows for future expansion if necessary, and the model has been split into parts to make it possible to 3D print, with pads and notches to allow proper adhesion between the parts.
Now we go back to Stanley for his final thoughts on the project.
This project has been a learning experience for me. I'm very passionate about the environment and exploring how technology can be used for us to learn more about the world around us. I employed new technologies and explored new tools which I was unfamiliar with, and overall I'm very satisfied with the results. I have enjoyed the process thoroughly. Looking to the future, I would like to see a similar system employed in a self-sufficient way and made available to the public on a larger scale to make environmental data accessible and available to everyone. Unlike existing commercial solutions, this system prioritizes educational feedback and affordability. The outcomes of this project contribute to research on accessible environmental monitoring and highlight potential for further expansion in educational or citizen science contexts. Thank you for listening.